Then the equilibrium of a particle presented also a few takeaways. The ones that we talk about, static equilibrium, and also we talked about dynamic equilibrium. And I mentioned to you that in most of the cases, things are in equilibrium, either they're moving or not. But for our cases in last lecture, particle was considered to be static in that sense. Also, we talked two important points were that the system of reference that you used in the solution of the problem would help you a lot depending on how you orient that system of reference. And secondly was that depending on how you chose to present the problem to yourself was something that was also going to help you. So meaning that there is not just one way to solve a problem, but you could always see that depending on what you choose to solve your problems, it could make your life easier. Now we're going to consider the case where the particle is moving, and we're going to talk about the kinematics. And if you see here in the presentation slide, you have kinematics of a particle, but you also have kinetics of a particle. The big difference between kinematics and kinetics is that in kinematics, we don't care what is originating the movement. We don't care about forces pushing the particle or acting on the particle to make the particle move towards a certain direction. We don't care about that. We are only interested to know the kinematics relationships between, or what's happened between the kinematics relationship, meaning velocity and acceleration, without taking care or paying attention or considering the forces that are producing that movement. However, when we move to kinetics, then is when we say, okay, now I have some forces applied to the particle, and those forces are going to make the particle move in certain direction or in certain way. There we take care about what are the forces applied to it. Let's continue. What we're going to see today are how to represent the kinematics of something, in this case a particle, in different ways. First, we're going to learn that, well, a particle, we are not considering rotation of a particle because the definition of a particle is something that has no dimension actually. It's difficult to express rotation in something that has no dimensions. The Euclidean definition of a particle is such that is a body, is something that all mass is considered to be at that point, but there is no dimension. So that's something that is very abstract in the sense of a definition of a physical body, but it allows us to simplify things tremendously when dealing with problems that could be simplified as a particle. Then we're going to talk about rectilinear motion, and we're going to talk about curvilinear motion in the sense that we're not talking about rotation, we're talking about curvilinear motion. And we're going to see here that there are different ways to represent that curvilinear motion. We have the XY coordinates that we know for sure how to do it. And when you see it right away, you are going to notice that, yeah, I know how the deal goes. I know what's the drill here. I know how to solve this. I know what's the procedure. Most likely, this is the way you have been seeing it before. Then we have the curvilinear motion in NT coordinates, and to refer to the normal direction here, and T to refer to the tangential direction. Then in a curvilinear motion, you have at least two flavors to choose from if you wanted to solve this problem. Lastly, for this curvilinear motion representation, we're going to talk about cylindrical coordinates, which refers to the coordinates r and theta. And this is pretty awesome or pretty convenient to be used for something called forced movements, where you know how the thing is going to go, and then the particle is going to move according to a certain prescribed motion that is being forced on the particle, meaning that there are extra elements or extra devices that are making your particle to move in that fashion. Depending on the case, this is the most closest to the nature of a curvilinear motion. This is the farther away from it. And the far we go from the natural description of a motion, more work is needed to be done to get to the same solution. And we're going to see that with a few examples. This is closer. It's farther. Now, let's take a look at these equations that you for sure have seen before. And again, the yellow box here means that these equations are going to be given to you during the exam, or you have it available in the formula sheet that is also download. You can download it from Moodle. So this is what is in yellow here. You're going to have it. And let's understand the rectilinear motion here. Rectilinear motion, as a simple concept, is just a particle moving, for example, in one direction or along one axis, meaning that if I have an XY axis here, try to draw it as straight as possible, then a particle moving, for example, parallel to one of those axes is considered to be in rectilinear movement. Now, you might say, well, what happens if a particle is moving, if I have another particle here and it's moving along this axis here, which is not aligned with the coordinate or Cartesian axis here? Well, the particle is also moving in a rectilinear motion. The only thing is that the direction of that movement is not aligned with the coordinate axis. It would make sense to do something here, like right down here, that, well, if I'm working with just this particle, and I have my coordinate system like this, so nothing stops me from producing another vertical Cartesian coordinate system or reference system like this, which takes the movement or the direction of the particle and aligns it with one of the axes of the new reference system, hence making my life easier when solving these problems. So rectilinear motion is that it just follows a line, straight line. Then when we talk about kinematics relationships between them, we have displacement, we have velocity, and we have acceleration. And we're going to be dealing with these four physical quantities as mentioned there, because these physical quantities relate to each other in ways that, in more ways than one. And that's something that we need to take care of if we want to approach a problem in the future with this. There is more than one way to do it. There is more than one way depending on the simplifications we take or we assume, and that's something we need to be careful with that. We know that if we have a particle that is displacing at some point here, there is a displacement or follows a path. If I derive that displacement with respect to time, so if I try to understand how that displacement changes with respect to time, then I'm going to obtain what is the velocity of a particle. The velocity of a particle, or the velocity in general, is a time derivative of displacement, and that's it. If I wanted to know the acceleration, then what I have to take is then go forward and derive the velocity with respect to time, and then I will obtain the acceleration of that particle. The simple or the one-time derivative of velocity with respect to time, I could use it to determine the acceleration, or if I have the displacement of the particle, I could straight away calculate the acceleration by taking the double or the second derivative of that displacement with respect to time. Things start becoming a little bit more, not complex, but more elaborate. And we need to take careful of this. We need to be careful with this. What questions do you have? Because this is going deeper and deeper as we progress. Are there any questions so far? Not so far. Okay. Again, this is important to mention that consider always that when we talk about this, how it is or how they are presented here corresponds to rectilinear motion. They might be similar to in circular motion, but we need to make sure that what we are using corresponds to the type of movement we are trying to describe. So try not to mix things, because if one equation works for one type of movement, it might not work for another type of movement. If we continue in rectilinear motion, it is possible to get rid of the time and describe our equations in terms of what is, oh my goodness, Haribol at Hikari. Could you please turn on your microphone? Please, let's be mindful of the people. If you're not going to say anything related to the lecture, please don't unmute yourself. Thank you. Remember, there is a key combination of keystrokes that would unmute your microphone, and it would be very annoying for the rest of the people to get to know what you're saying, for sure. Then let's come back here. Then if we can get rid of the time because something that it doesn't appear or it doesn't matter to us to take into consideration time, then there are certain relationships that we can take as acceleration can be put in terms of velocity by just using intermediate, let's say, help from the displacement without taking into account time. And now this is a very interesting slide because it talks about velocity as a vector, but it also talks about speed. Now, if you read this carefully, you say, okay, speed is scalar and only has a magnitude. That's perfect, I know that. Velocity is a vector and hence has a magnitude and a direction. But if I want to say something like, okay, the speed of the car is 40 kilometers per hour. But also, this is the speed of a car, but I could also say that the velocity of the car might be 4 kilometers per hour at a certain direction. Then what's the difference between speed and velocity? Because they seem to be pretty similar in concept, or you might assume, well, speed might be considered just as the magnitude of the velocity, but that's not completely true. There is a fundamental velocity difference between velocity and speed, and that fundamental difference comes from how they are calculated. Speed is related to distance traveled, while velocity is related to displacement of a particle. There are two very different concepts. Distance travels is something like, for example, if you go from point A to point B, you traveled a distance of 10 kilometers, or you traveled a distance of 5 kilometers. But displacement, you could be traveling around and have a displacement of 0. Then the fundamental difference lies on how those two terms are calculated. And one has to do with displacement, and the other one has to do with distance. Here in the figure, you can see, for example, if we wanted to calculate the average velocity and the average speed of what happened there, the average velocity only takes into account, for example, this small segment here, traveled here, but the particle P might have gone to a certain point and returned back to here, which means that it traveled a certain distance. So this average speed is completely different from the average velocity or the magnitude of the average velocity. So when we talk about speed and velocity, there are two different things. They could be the same at some point, depending on how the particle is moving, but fundamentally, they are not the same. So we need to be mindful of that. What questions do you have about speed and velocity? Is it clear that speed is not the same as velocity? Why is this important to know? I have some said average velocity is displacement divided by time interval of the displacement. Yes, that's correct. Yeah, perfect. This is important to consider when you are given some information to solve a problem or an exam or an exercise or real life. If you're given information on a speed, you know what comes from it, or if you are given information from velocity, then you know how that was formed, how that was calculated, so you know what's involved in the term they are given to you. So that's why it's important to know the difference between speed and velocity. Great. Now, this is some sort of help in terms of, okay, if I'm given these physical quantities, what can I calculate or what can I do to find another thing? So it basically says that if we know the dependence between two of the quantities, A, B, and S, and time, then we can solve for the third one and so on. For example, if we know displacement and velocity and time, we can calculate velocity, hence later we could calculate acceleration. But again, these are formulas that are repeated again here that corresponds only to in terms of rectilinear motion. They might be the same for curvilinear motion, but we need to be careful about that because sometimes they don't match each other. Then if I wanted to make some sort of path here to follow when trying to solve these equations, if I have displacement and I differentiate this with respect to time, let's put it in that way, I can get velocity. And then if I differentiate this with respect to time, I can get acceleration. If I wanted to go back, meaning that if I have acceleration and I want to get to know the velocity, then I have to perform the integration of the value there to get to velocity. And then if I have velocity and I want to know the displacement, then I would have to integrate that velocity to get to displacement. So moving forward, naturally, we have to differentiate or take derivative. And on coming backwards from acceleration to displacement, I have to take integration. Also, I believe it's a pretty well-known procedure that you have seen before. Let's see. I have a question here. I didn't have derivation and integration during my high school studies. What should I do? Will I manage or do I need to take some extra course? Thank you. Yeah, this is a very important comment because we have been discussing this in the past weeks with the difference between school systems around the world. And I'm on board with you because also when I took my high school, I didn't see any kind of integration of derivation actually, or if I saw them in classes were really mild or they were non-important actually for university studies. This is something that in the course or in different courses for sure you're going to be facing integration and derivation. And here in these slides you're going to see that we're going to integrate and we are going to derivate. Hence, my only suggestion at the moment is if you can find extra courses or try to learn the basics of derivation and integration, that's going to be pretty beneficial for you because most of the core concepts that you're going to be seeing here, and even when you go to, for example, vibration, something in this phase here, vibrations, that's something that you are going to need definitely to know integrations and derivation. And also when we talk about work and energy and impulse and momentum, those terms, work and energy and impulse and momentum, are solely defined based on the integration or derivation of certain physical quantities, meaning that my strong suggestion is that you try to, on the side, try to go and learn what is derivative and integration because you are going to need it. You're not going to need it as a strong mathematical background, at least at the beginning, but that's something that's going to benefit you. So that's my only suggestion here. And I know it's complicated because, no problem. It's not, it's complicated because most of these problems that you're going to see here require that you derivate and you integrate. They are pretty basic level 101 integration functions or norms that you can take, but you're going to need it. I hope that it's going to be difficult sometimes then to understand or to get the idea of what I'm doing or what is presented in the content if you don't know that core concept. But try to go, start from today. Try to go and see how to. I'm not kind of. It's not actually. You can go even to YouTube and start looking. Okay, how do I integrate? How do I derivate? And start from it because you're going to need it. And it's better if you take it right now. And for sure, with all the knowledge that you have accumulated so far, it's going to allow you to use those skills to get the grasp of what an integration and derivation is. All right, so let's see this example. It says, a car is moving in a straight line and its velocity is defined by an equation. V equals to which one? 0.9 t squared plus 0.6 t meters per second. If we define that when t is 0, also s equals 0, determine the position and acceleration of the car when t equals 3 seconds. Okay. Let's see what we have here. At the beginning, the car was here, and this corresponds to t equals 0, meaning, well, definitely time is not never, we're not experiencing time equals 0, but the beginning of this movement, the time 0 for this time for the beginning time for this movement was 0. Then the car was here, but now the car is at a distance s that we don't know which was it, but they're asking us, okay, but now when the time has elapsed is 3 seconds, tell me what's the position of the car and what's the acceleration of the car. Then, yeah, well, you want me to tell you what's the position and acceleration, but you are only giving me the velocity of the car represented by this formula here. I got one comment in the chat. Matesh, he shared a YouTube video. I assume that corresponds to integration and derivation. If so, thank you. Now, remember this piece of formula we have here that says, or the process here, that if I have something, I have to either integrate or derivate to find the other ones. Thank you. Thank you for that course, or the link to that course. So then, if I have only this represented by this formula, and they're asking me, okay, tell me about this and tell me about this. That meaning that if I wanted to determine the position of the car, meaning s, I have to integrate the velocity to get to the position. If I wanted to know the acceleration of the car, I have to derive the velocity to get it. So let's start with the first one. If I know that the acceleration is the time derivative of the velocity, and then I have the equation for the velocity, which is given in the problem, then the derivative of this point is this one. And sorry about that, that you're not going to be able to follow completely this, because this is important. But basically, in this simple term, what you do, well, it's going to be hard to explain how to derivate on integrating this course, because it would take so much time. But I hope that you bear with me and try to look at those courses or that course. So you have a acceleration. What does you mean? What did you mean by acceleration? Okay. So when I take this derivative, I get the formula for the acceleration here. And when I get this, it says, okay, now if you want to know acceleration, just use this equation here at a certain time. So it's not going to be given here, but I know that if I want to know the acceleration when time equals 3 seconds, then for sure, having this equation, I can just input 3 seconds here, and I would have the value of the acceleration. Yeah. If I want to do the same with the position, then I have that position is the you have to integrate velocity to get the position, and the way you do it, or you get to that reasoning, is that, okay, I know that velocity is the derivative of position with respect to time, and that's this result, which is given in the exam. But now, let me see. For the acceleration, we need to differentiate, and then we have, yeah, that's correct. And then when we take this integral here, okay, No, it's not a stupid question. It's a very clever question, actually. And it's glad that you notice it. So, yes, when you integrate, remember that when you do integrals, you have two types of integrals. You have the definite integrals, and then you have the undefined integrals. Let's put it in this way. When we talk about defined integrals, then you have boundaries here. You have upper limits, and then you have the lower limits. Then when you do this, you don't have to use a constant because you are bounding your calculation or your integral. Now, if you didn't have any of these two boundaries, upper limit and lower limit, then you don't know what are the bounds of that calculation, and then you have to give a margin of something here represented by that constant. So that's why in our cases, or most of our cases, we don't use an integration constant because our integrations are bounded. So they're definite, or their boundaries are known. No problem. Yeah, that's the two cases. So when you see something without boundaries, put the constant next to it to accommodate for that. And when you see boundaries, you don't have to use a constant there. Then if I move this to this position here and I want to know the position, then I have to integrate. That's why it appears in this fashion here. Then, if I integrate, I have to use boundaries, which I know, and say, okay, I want to know the position from the starting point, which was 0 at this point, until it gets to a certain point S that I don't know. And then you have to tell me, okay, now, if you want to know that position at the end, you have to integrate the velocity with respect to time, and then the velocity goes from 0 or time 0 until time t that you don't know maybe, but yeah, you do know because it's given here. When you perform the integration of this, it remains just s. When you perform the integration of this term here, it's a pretty simple integral, so you come to this result here. When you apply the boundaries of the integrals here, or the bounds of the integral, then you end up with this formula here. Now I have a formula for the acceleration, and I have a formula for the displacement here. What's next? Well, if I wanted to know what the acceleration is and the position of the car is after t equals 3 seconds, then I have just to input 3 seconds here, and I have just to input in these two parts here 3 seconds. And that's what is done next. Substitute 3 seconds in each one of those equations, and you get that by 3 seconds, you're going to have 6 square meters per second in acceleration, and those same 3 seconds they're going to have that the car has, let's say, moved or traveled 10.8 meters. Now, this is a pretty standard problem that you're going to be seeing, and you notice now that to give answer to each of these questions here, in one you had to derivate, and the other one you had to integrate. Very simple integration and derivations, but you had to do it. So again, yeah, some work is going to be needed, extra work is going to be needed to get the grasp of what integration is and integral is. Questions so far? Now, there is a workaround for to avoid integration, and is that if our acceleration is constant. In that case, all of the equations that you have there can be presented in a pretty standard form. And if the acceleration is constant, remember, this is something to be careful with. Only if and only if the acceleration is constant, meaning its value doesn't change. And let me expand that concept. If the value of the acceleration is a vector has magnitude and direction. If the acceleration doesn't change either in magnitude nor in direction, meaning that it's constant, then you could apply these formulas here. And most practically, you are going to be able to apply these formulas when you try to decompose the problems into X, Y, say reference system or something like that. But always, again, the formulas that were presented so far are formulas for rectilinear motion. They might work for curvilinear motion, but you have to be careful with that. And also you can simplify, meaning you could avoid the integration of any quantity and maybe some derivation also, if and only if the acceleration is constant. If it's so, you could maybe use these equations here. Yeah. And this is a note that Olli Pekka put here because this is true, and actually I have fallen for this in my times, that these are pretty straightforward formulas that they look pretty simple to apply, and they, at first time, they make sense, and that, yeah, this is the way it should go. But careful with this. This is very important. Only if and only the acceleration is constant. There is another way that we could approach problems, and is from, if I could say it, the type of graphical point of view. When we take integrals of a formula of an equation, what we are basically is calculating the area of under the curve. So I have the integral of the function that changes with respect to f, and the integral with respect to x. So this blue line here, or this line here, is kind of something that is moving at a certain way apart and described by a formula or an equation. Basically, an equation. And if I say, okay, I want to split this equation into two parts, meaning between these two boundaries here, this one and this one, which are these boundaries here. And I take the integrals of these, what I'm just doing, it sounds simple, but maybe it's not, depending on what's the shape of this function here. If I take integrals of that, then what I'm just doing is calculating this area here. The area under the curve bounded by those two limits or integration limits. So meaning that imagine that this is the function or equation for velocity, for velocity, or let's put it acceleration. And I take the integral of this, what I'm calculating is the velocity, something like that. And also imagine that this is the velocity, or these curves represent the velocity of a particle with respect to time, or with respect to this variable x, and I take the integrals between these two limits. What I'm going to calculate is some sort of average displacement, because when I integrate this velocity here, this is basically giving me the area under the curve here. This is a way that we could approach problems. And actually, in the demo lecture that's going to be released for you today, you're going to find that one problem can be solved either using formulas, or you could use a more graphical approach like this and use areas to calculate displacement, velocities, and acceleration. Sometimes it makes our life easier to do it in this way as it is presented right now, but some other times, well, you have to decide what to use and not. All right, so let's see another example on rectilinear motion. Things are getting a little bit more, let's say, deep. We have a motorcycle and it's in rectilinear motion, and we know that because it says that it's driving on a straight line. So actually we don't even care to draw the XY axis or reference system because it's a rectilinear motion. So we would assume which formulas to use and how the deal goes. Then it says, now with the motorcycle is also presented a chart. This chart draws the velocity versus displacement curve. So we have one first area where actually the velocity value changes with displacement in a rectilinear or a line that is stepped or have a slope here, and then that line becomes totally horizontal here. Now, without knowing anything about formulas to apply or what to do next, if I wanted to try to understand what's happening in this chart, I could say, well, I know that from 0, which is this point here, to 60 meters here, the velocity increases from 3 to 15 meters per second at a rate of 0.2 seconds per minute, something like that. This is the equation of a straight line. This is the slope intersect form of the line equation, of the equation of a line. It's not the canonical one, it's the slope-intersect equation of a line, where this here is the rate of change, also called slope, and this here is the intersect, which is the point that the line touches the vertical axis, which is 3. That's why 3 here. So this form of equation that you are going to see written several places, like y equals to mx times or plus b, this is the slope-intersect form of the equation of a line, where this is a slope, or the rate of change, and this is the point where the line crosses the vertical axis, or y in this case. So yes, from 0 to 60 meters, the velocity is increasing, but from 60 meters to 120 meters, the velocity stays the same. And if the velocity magnitude, we're seeing magnitude here, stays the same, we can say, well, if the velocity is constant, well, we might infer what's going to happen with certain other physical quantities, such acceleration. If I know that the acceleration is the derivative of velocity with respect to time, and this doesn't change with respect to time because it's fixed as a value, then this is going to be 0, meaning that acceleration in this stage here is going to be 0. So that's something that we can already tell from the problem without doing any step to solve it. The first request that is made is construct the AS graph of motion. That is, I'm going to have, let me see if I can draw something like home, insert, something like this. Let me see. So meaning that I have to have an axis here, and I need to have another axis here. But now instead of being v versus the velocity versus the displacement, I need to have the acceleration, most probably in square meters per square second, times the displacement here. So how is this going to be here? I don't know. We need to find out. So that's the first request. And the second request is, how long time does it take for the motorcycle to drive 120 meters? So what's the time for this? So how long does it take to go from 0 to 120 meters? And those are the two things we need to find out with the tools we have so far. All right. Now, it makes sense to split the case into two parts, because I know that something's happening between 0 and 60 meters and something else is happening between 60 and 120 meters. In the first stage, from 0, when the displacement goes from 0 to 60 meters, I know that the velocity of the motorcycle in that stage is this one, which is given by the equation of the line here. It's 0.2 s times 3. Now, if I wanted to know the acceleration of the motorcycle in this stage here, only in this one here, then I would need to take the velocity and derive that with respect to time. But we don't have time here at all. So how could we do? Remember that we have certain formulas that would say that, let me come back here a little bit more up to show you and bring it down, that sometimes when we don't have time, we might use this reference where acceleration and velocity are related using the position or displacement of the particle. Well, we could use this one. And then if I take from here, for example, the acceleration and leave this term alone, I could say that, well, v times acceleration equals to the velocity times the derivative of the velocity by the derivative of the position of this. And I could use this if I don't have time anywhere to try to solve for this, which is what is done right here. Okay? This is the same equation I had just shown you. Then I just input the velocity here, and then I try to perform the derivative of that velocity equation with respect to displacement. And it makes sense because velocity is expressed in terms of displacement, not in terms of time, meaning that I could take the derivative right away there without doing any type of modification or change at all. Then I derive just this part here and doing this derivative and then multiply that times this one, it would result in this final equation here. Then acceleration equals to 0.04 times s plus 0.6. Great. And again, look at the form of this equation here. So we found the acceleration in terms of the, let me write this a little bit better, s here, in terms of s. And this also presents some sort of resemblance with the equation of a line. Remember, equation of a line is the slope times the variable you are, say the known, unknown plus the intercept here, where this one is this one and this one is this one. So yeah, there's something pretty similar here. And then in this term from 60 to 20, 60 to 120, the velocity is constant or is kept at 15 meters per second. And if I take the derivative of a constant, the derivative of constant is 0, in this case the magnitude, then rendering everything to 0. Then what's going to happen? Well, here what you kind of assume that you have. So the acceleration is going to be 0.04 times s. This is the slope. This is the rate of, say, change of that acceleration with respect to the position. And look at this. How to draw this then? Okay, you are giving me this line here that says the acceleration equals to 0.04 times s plus 0.6. So let's remember that this is the intercept point of this equation with the vertical axis. Look at this. This is the 0.6. That's why it's appearing here. And then I know that if I input 60 here and multiply it by 0.04 plus this much is going to give you these 3 here. So I can identify these 2 points pretty easily. But then in the other segment from 60 to 120 meters, as the acceleration is 0, then everything kind of drops to 0 and stays in 0 like that. So now we have given answer, or we have given the answer to the first part A, that says construct the AS graph of motion. And it looks pretty weird, but that's the answer to this one here. So we migrated or changed from the velocity versus displacement to the acceleration versus displacement here. And what it says here, yeah, even though, remember what I told you in the past about displacement, position, velocity, and acceleration. Position tells you where a particle is. Velocity tells you where the particle is going. And acceleration tells you where it would like to go. So that's beautiful to see that, for example, in the first stage, yeah, the acceleration keeps doing this. The acceleration, you have some certain acceleration, very small, but you have it there. But then after the end, you are not applied any acceleration, meaning that in an ideal world where there are not resistance forces or anything, this would mean that if nothing is done here, this motorcycle would continue just moving in this direction forever and forever. What questions do you have? Now, from a mathematical standpoint, we have used a couple of things here. We have used integrals, derivative, and also we have used the equation of a line, which pertains to geometry. So that's something that you see that gets, if you wonder yourself when, again, would you be using, for example, the equation of a line in your future? Well, you're going to be seeing it right now a lot. Part B, how long time does it take for the motorcycle to drive 120 meters? All right. So let's see how we tackle this. This stems from the fact that velocity we know is the derivative of the position or displacement with respect to time. Yeah, time is nowhere to be found here, but I know velocity and I know displacement, meaning that I could take this away from here and say, you know what? Yeah, I can move this up, and I can say that, you know, the derivative of time is equals to the this these variations of displacement divided by the velocity. All right, and this is what is done here. Then if I substitute the formulas, I find myself that if I wanted to know how time changes or what are the values of time in the whole movement, I would have to integrate this equation here. So this one here and this one here, what is done here. So I want to know what's happening here. Now, this only applies from 0 to 60 meters. So this is valid only for this segment from 0 to 60 meters. The integral of this term here is pretty simple, it's pretty straightforward. However, the integral of this one starts becoming a little bit more complicated because it involves the natural logarithm or certain magnitudes and certain rules that we have to follow. But having that, after integration and application of the upper and lower limits, we find that the time can be described in terms of the displacement of that motorcycle in the segment from 0 to 60 meters by this equation here. Meaning that if I know that in t equals 0, the displacement should be 0, but in displacement, the displacement is equal to 60, then how long does it take, did it take for the motorcycle to go from 0 to 60 meters? Well, from 0 to 60 meters, it took about 8 seconds to reach from here to here, or to this point here. So this is this 8.05 seconds. But now what happens with V, with the segment from 60 to 120 meters? Well, we do more or less the same. So from 60 to 120 meters, I know that the velocity is constant, and I just can apply this type of integrals here. But now notice something that is pretty important to consider. We're talking about a problem that is divided into two stages. The first one here that has a velocity change in a way, and then the other one here that has another velocity, not change, but behavior from 60. Now, in the first integral, my integration limits were from 0 to t, meaning that t was, if this is the t-axis, 0 here was 0, and then t equal to 8.05 here, seconds. But when analyzing this segment here, I don't start from 0 because some time has already elapsed. That's why the lower limit for the time is not starting at 0, it starts at 8.05, which is the answer I found before. And that goes to a time t, that's the one that we need to find out. Then the displacement goes from 60 because it doesn't start at 0, it starts at 60, and it goes to a certain value here. That most probably we are going to know that value, or interest value for us, is going to be 120 meters. But we're going to keep it as a variable here just to have a general representation of that equation. But definitely it's going to be 120 meters. If I make the integral of this, it's going to be also, and making the integral, integrating and applying the boundary conditions or the boundary limits, I'm going to have that this segment is this. And again, planting the boundaries here is going to have something like this. Meaning that if I wanted to know what's the time when the motorcycle has reached these 120 meters, is that I have to input my target displacement here, which is 120, and then that's going to give you this 12 second. Then if I make this a line here, it says, well, 0 to 60, it took 8.05 seconds. And from here to here, it took the remaining something, 3 something. So it took 12 seconds to go from 0 to 120 meters. And the key part here was that the boundaries used, or the limits used for the integrals, are well framed in what are these segments here from 0 to 60 and from 60 to 120. Careful with this. What questions do you have? All right. Now let's complicate things a little bit. Did you round down? Might be, I'm not sure. Again, coming back to this discussion about how many decimals you use, rounding you do. I would say that as long as you're not off by, meaning that if your answer, or if the, let's call it in this way, if the correct answer is 12 and you come with 11.9, something like that, so that's not going to be an issue. Or 12.15, that's not going to be an issue, okay? So, but if you come with answers such as, well, the answer is 12 and you come up with 10.5, so that's a no-no. So coming back to that discussions about how many significant figures you should use and when you should be rounding up and everything, yeah, well, just try to round up at the end. If for the intermediate figures, you can use up to 4 decimals if you want, but as long as you are close to in the vicinity of the answer, so you shouldn't have any problems there. Again, in this case, it might be that it was not rounded, or yes, because I didn't solve this exercise or put it here. In this case, 10th of a second. What do you mean by that? You mean as a difference between the correct answer and your answer? Is it? Well, it's very, let's say, it might be, but don't be so rigid on this. So for sure, if you have certain, if you're in the vicinity of this, I just put this as an example. It's not a strong guideline on how different it should be. Just try, just if you're in the vicinity of this answer, it's going to be fine. So what I could do is kind of to try to model what is done in the exercise sessions, for example, because in the exercise sessions, I assume that the teaching assistant is trying to solve everything step by step or showing you how to do it. And then you get to see the pattern on how they are handling the intermediate results and how they are rounding up or down the final results. So try to emulate what they are doing and most precisely ask them the question, because in the end, they are going to be the ones who are going to grade your exercises. And when Olli-Pekka comes back to teach you in the second period, ask him, well, how rigid is him, and try to follow his way of doing stuff. In my personal case, in my course, if you are close to that value, for me, it's okay. It doesn't have to be 12.0. It could be, I don't know, 11.7. Actually, for example, in my course that we deal with strength of materials, which goes a little bit more advanced in what's happening in the mechanical world or mechanics world with elements or machines. If, for example, we are designing a column, imagine that this is a column and this is holding some weight, this is grounded, and you have a weight like this, for example, here, applied to the column, then the natural, let's say, way that this column might fail, meaning that crash, might break or deform, is that this kind of bends like this or deforms like this. And then most of the questions associated with just a design of columns is, what's the maximum P that you could apply here that this doesn't fail, let's put it in that way. And imagine that the true answer is, I don't know, 1,500 newtons. And you come with an answer of 1,480 newtons or something like that. It's okay, because what I explain in my course is that these values are so over exaggerated that missing a few tens of newtons in one answer is not going to make a difference. And I explain that in detail in my course on how we engineers consider safety in our designs, how we dimension, let's say, the materials, how we select the material, which type of steel we use, how the forces are applied. And then when we go over the whole change of decisions to be able to calculate or design something, you're going to realize that if you miss a few newtons here, it's not going to make a huge difference in your result. So, but my recommendation for this now is that you see how the teaching assistants do the work with how they work with the intermediate results, how they round up or down the final results, and when Olli-Pekka comes, then you can decide on how to approach the problems in your own terms. Now, the infamous curvilinear motion in x and y coordinates. Now, this case is when our particle is forced to be represented on a x and y coordinate system that we have to use components. Now, that's why it's important that we saw how forces are decomposed, because forces are natural, they are vectors, velocities are vectors. Then we could use the same principles applied to forces or force composition to be used also with velocities and accelerations, which are vectors also. Now, if I have a velocity and acceleration that has two components, I know for sure, or I know now how to calculate the resultant of that velocity or acceleration by using this Pythagorean theorem, which are presented like this one. And again, these are in yellow because they are given to you in the exam, or these are going to be available to you when solving the exercises or solving the exam. And again, let's remember that when we wanted to know the orientation of that vector in that XY reference system, we used those components and the inverse of the tangent to calculate those angles. And again, the convention we used, it was that our angles are always measured starting from the x-axis. Remember that we have been carrying that from lecture number 1. Angles that we use to represent our equations are measured always starting from the x-axis. That's why we can standardize the way we write these angle formulas here. Now, remember that we talked about the farther I go from the nature of the nature or the representation of the problem, the most complex it goes. Well, when should we use XY coordinates? Usually, the most typical case to use XY coordinates, and it would make our life easier to do so every time you see it, is when we are in the presence of a motion of a projectile in the air. And not only a projectile, but anything that kind of simulates that type of movement of a projectile in the air. And for that, we have this example here. This is not a projectile, but these are particles that are kind of fired from this tipping machine skull, and they land at a certain pile here. And let's see what it says, and let's try to analyze this problem before starting the solution of it. It says, the chipping machine is designed to eject wood chips at an initial velocity of 7.5 meters per second, meaning that at this point, look at this point where we have fixated the XY reference system here, already here at 0x, the velocity of the particle in this direction, meaning oriented 30 degrees with respect to the x-axis, is 7.5 meters per second. Just at point 0 or time 0, let's put it in that way. The tube is oriented at 30 degrees from the horizontal plane. Again, this complies with the convention we have been using in the past, that most of the angles, or almost all of the angles we're using to write down our components in our decomposition process, start from the x-axis. It says, determine how high, h, the chips hit the pile if the pile is 6 meters from the tube, meaning the starting of the tube of the machine is here, and the pile, let's put its center, is here at 6 meters, and then it says, okay, how much is this? How much it hits this pile at 6 meters? And look at this, we are not talking about time at all here. The only thing we are knowing is that the distance from The x-axis to the ground is 2.1 meter. This pile here is at an h distance from the ground, meaning they have a common reference. But they're asking me what's the y position of in A? What's y in A? So that's what they're asking me, basically. So they're asking me h, but what I need to find is ya, this position here at point A, the vertical position, which is this one here. And by having this position here, then I get to know h. Why? Because I know that, how much is this ya? If you subtract, for example, h minus 2.1, sorry, meters, that's going to be equal to ya. So meaning that's why I need to focus on finding out what's the position of the particle here, that which is measured according to this reference system. And then using that position, I get to know how much is h. I hope it makes sense. Let's continue. Now, first step, we decompose the velocity into x and y directions. So meaning that x direction goes to the right, is positive. It would make sense, I have a comment here, 2.5 minus h. It would make sense, and you're correct, and the logic says that. But remember, when I go from here to here, I'm walking a negative path, meaning that the value, most probably, of ya is going to be negative. Do you agree with me? And if so, then it would make sense to do it this way as I'm presented it here. Yeah, yeah. You could use that, just keeping in mind the signs you're using in your reference system and how you can accommodate that. Great question. Then I know here that the horizontal component is positive going to the right, vertical component is positive up here. We're doing it right now. I don't know if my video is lagging, but what we're doing right now is finding the components of the velocity. Here. Yeah. Yeah, so we have the components, perfect, not a sweat. We already know how to do it. We are masters of this, so no problem. Let's see, what next? Remember that if the acceleration is constant, we had certain simplifications of our equations, meaning that we didn't need to integrate anything, because if the acceleration is constant, then it would be easier for us to apply certain formulas. But what about if the acceleration is zero? Well, it falls also in that representation. Let's go back to it. Let me see if I can find it. Where are they? Here it is. Here I have one in the position, meaning that, for example, if the acceleration is zero, this term would be zero, something like that. And then it would make sense to apply this. Then I have time. So you see, now we have to be careful with the formulas that apply or do not apply here. So if I have half here, kind of the same one that we're mentioning here. So we have that the final position in the horizontal direction is going to be equal to initial position plus how much time has the velocity been affecting the particle. Let's put it in that way. Now, I know that our movement starts at 0. So this is x0. This is xa. Then xa is 6 meters. X0 is 0. And then the velocity we have found, the horizontal velocity. Horizontal velocity. I don't care right now. I have split the velocity into two components, and I'm just focusing on the x-axis. If that's so, then that's allow me to say, you know what, the only value of velocity that matters to me is the horizontal component of it, meaning that by just having utilizing these simplified equations, I get to know how much does it take for this particle to reach from x0 to x8. And it says that, well, it takes so fast here, isn't it? 0.9231 seconds. Wow. Okay, now I have found one value for time. Now I know how long the particle took to go from this point 0 to this point A. So it flew all this time to get here. Okay, now I notice that, well, I used the acceleration in x direction, meaning that I exhausted my resources in the horizontal axis. Well, let's move now. Let's see what the y-axis or vertical axis has to offer. One thing we should have present all the time when we are dealing with particles that are flying, like these ones, like projectile-like movement, unless said otherwise, is that the acceleration in the vertical direction is going to be gravity here, and it's going to be constant. Then coming back to those equations, I know that the position in A, the one that we were discussing before, to be able to calculate that, is this very same shape of formula. The only thing is that the term related to acceleration was removed because there is no acceleration in the x direction. And in real life, there is some sort of acceleration in the x direction that is related to friction, for example, air friction. In this case, it's an ideal case, so we are just considering that there is nothing in the horizontal axis that is stopping that particle from flying. That's why we can say that no acceleration in the x direction. But now, in the y direction, yes, we are in the presence of a gravity, and these terms that disappear in the horizontal axis is present here. I have a time, I have an acceleration time, I have a velocity in y, I have a starting point here, and definitely I can find how much is this position ya here. And you see now that that y is giving you in this shape because we are considering that this is negative, and then this matches beautifully what we're trying to describe here, meaning that in this case h equals to, when solve this equation, which is just pure substitution, this is something that we are going to have here. I have a question here. I'm going to answer it in just a second. H is equal to 1.38. Questioning, how did you get that acceleration y direction? Yeah, so whenever you see this type of problems, which are, let's say, some sort of free flight, projectile motion, any particle flying in reality is going to be subjected to the weight affected by the gravity, right? This gravity is acceleration, the vertical acceleration. And then, as said or mentioned otherwise, always whenever you are in the presence of projectile motion or free flying motion, then there is an acceleration acting on the particle, and acceleration is going to be the gravity, minus 9.81 pointed downwards. So that's where I get that. Unless the problem is specified that, what take as vertical acceleration this quantity, then you take that quantity. But if not, definitely you know that any particle flying in the air is going to be subjected to gravity, and the acceleration of gravity is going to be this one here. That's how we got it. No problem. Another question says, can you show the original formula from form you used for YA? It was in the previous slide. You mean this one? If it's this one, or the one that is already considered as constant. Okay, this one. Okay, yeah, no problem. Great. Let's see where we were at in here. Yeah. Then it says that, okay, the height of the pile is going to be 1.38 meters. Locally, there was no any integration of derivation because we're in the presence of constant velocities or zero velocities. In the case of the x-axis, we could use straight away those formulas and get the results we wanted. And again, heads up, whenever we are using free flight, whenever we are in the presence of free flight, then gravity is a vertical acceleration if we use a reference system oriented in this way. Let's see. How YA? Could you elaborate in your question there, Bindu? It says how YA? Could you complement that, your question? Because it's really open to answer many, many things. Nope? Okay. Now, curvilinear motion in normal tangential coordinates. This is where the thing gets trickier. And actually, we touched on this in the past class, I think. Because acceleration as a vector has a magnitude and a direction, and usually acceleration is not as nicely behaved as velocity. With velocity, we don't have any issues. So let's put it this way. If I have a particle moving at a circular or curvilinear path, something like this, I know that velocity is always going to be tangential to the path, meaning that I could draw a line like this. Let me see if I can put this ruler here. As tangential as possible. So is at that point, the tangent line to that particle, tangent line meaning the line that touches the curve in just one point, then I'm going to know that the velocity is always going to be oriented in that direction, parallel to that line, and it's going to be pointed at the same direction of movement, meaning that if the particle is moving in this direction, then the velocity is going to be moving in that direction. But the acceleration, as the acceleration is the derivative of b, sorry about this, of b with respect to time, why acceleration has two components, tangential and normal? Well, because let's remember that we are taking the derivative of a vector, not of a scalar quantity. And when we take the derivative of a vector, we have to derive the magnitude, let's put it in this way, with respect to time, and derive the direction with respect to time. And when we do this, the acceleration comes up or appears in front of us with two terms, the tangential term and the normal term. Then that's why you see that, for example, the tangential of component of the acceleration is this one here is aligned with the tangential, the tangent of the whole, let's say, movement at this point, also aligned with the velocity. But it might be that it doesn't have the same direction, meaning that imagine it could be that the acceleration of this, let's say, the velocity of this particle is pointing in this direction along the tangent here, but it's not to be surprised that it might be possible that in some calculation cases, depending on how the movement goes, that the acceleration or tangential component of the acceleration goes in the contrary direction of the velocity. And it just means that it's decelerating in that component. So the acceleration might go in the same direction of the velocity or contrary to it. But the normal component here is always going to point at the instantaneous center of rotation. Now, be careful, this is a mouthful, instantaneous center of rotation. Why? Because in this point here, if imagine that this was a circular, perfect circular movement, then this would be kind of the radius and it would be the center of rotation. However, if the particle was here, then the center of rotation might be around here. Let's put O2 primes. So that's why we call it instantaneous center of rotation when we are in the presence of a path that is not perfectly circular, but is curvilinear. So this is the instantaneous center of rotation because it changes at imagine that every second that that particle is moving, there's going to be a different center of rotation. And you have to consider that in your calculation. But the normal component of the acceleration is always going to point at the center of rotation, always. What questions do you have? Let's continue. Then curvilinear motion, continuing in these normal tangential coordinates. Yeah, the tangential acceleration or the tangential component of the acceleration is the simple derivative of the magnitude of the velocity with respect to time. And the normal component of acceleration is this term here, which is the velocity at that point squared divided by this rho here, which is the radius of curvature. The radius of curvature is to say this here, so the distance from here to here, or the distance from here to here. That's the radius of curvature. And what mentioned, if our path is perfectly circular, then the radius of curvature is constant, which is the radius of the circle. But if we're in the presence of such figure or curve like this one here, then we need to find a way to calculate that radius of curvature at each step. And there is a formula for that, which is this one here. Now, remember that we said that, for example, the derivative of f(x) with respect to x, for example, or the derivative of a function can be represented or written like this. This is equivalent as notation form to be written like this. So if you see this, it's equivalent to this. So this is the derivative of this function f with respect to x. This is also the derivative of this function f with respect to the variable that is inscribed here in parentheses, which is x. So this is this thing here. And this term here is the second derivative of that function with respect to this one here. So they are different ways of writing the same thing. Writing it with the apostrophe here, it makes it more of a compact notation, but it means the same. But this has some consequences in the sense that if I wanted to know the radius of curvature of a path, curvilinear path, like this one, I need to know the path. If I don't know the path, then I cannot calculate this, making everything more complex. So definitely in a problem where you are going to be required to use this formula to calculate the radius of curvature, yeah, maybe the concept of center of rotation is a little bit more, let's say, far away from this, but applies also because this is not rotating, this is just displacing, but the concept, the premise is the same. But if you have to have this, then you need to know the path to calculate everything. And I guess in the example that comes next, we need to use the equation describing the path so we can know what's the radius of curvature at that point. What questions do you have? All right. Let's see. It says a skier slides down a parabolic path. You see, now they're telling us what the path is. It's parabola. And has a speed of 6 meters per second, which is increasing at 2 meters per square second. Let's stop that. So they're telling me that that skier is at that moment this moving along a path, that path has a certain, let's say, characteristics, and it's written here. So the path that is following the skier is this one here. So it's a parabolic path because this x squared, so it's just typical representation of a parabola. Then it says at this point it has a speed of 6 meters per second, and then and that speed is increasing at 2 meters per square second. What is this? So this is related to this. If this is the speed, the interesting term here, speed, what means that that speed is increasing at 2 meters per square second? Well, any change on that value is what? Let's remember the acceleration is the change of velocity with respect to time when we're in the rectilinear motion. And when I give you any information about how the velocity is changing with respect to time, then I give you the acceleration, meaning that at that point, this is a value of acceleration. Right. And then I also know that at this point, it is the skier is at 10 meters from this horizontal or 0 point origin of the reference system and 5 meters in the vertical direction from this origin of the reference system. What are they asking? They said, determine the direction of his velocity and the direction and magnitude of his acceleration at this instant. So this is very awesome. When you are facing this type of problems, imagine that this skier is moving. Yeah, so, and then while moving, you took a picture of the skier at that instant. And then you are asking yourself, hey, I took a picture of the skier. This is the reference point position of the skier at this moment right now. Tell me now, for this picture you took, what's the velocity and what's the direction of the velocity and direction of the acceleration of the skier at that precise moment. It doesn't matter the rest. It doesn't matter that it's coming to a horizontal face here. It doesn't matter that it's following a certain path. Nothing. It just matters that at that step, tell me what's the direction of the velocity and the magnitude and direction of the acceleration of the skier. Right. Let's see. One thing to notice is that if I'm talking about tangents, tangents form an angle. The tangent of this skier at this moment is, we try to draw in red. Would it be the case? Yes. So this is the tangent, considering the skier as a particle. And this tangent forms an angle theta with the x-axis, which follows the convention we have been using before. So one of the first questions that you would naturally ask is, okay, what's the value of this orientation here, of this angle here between the horizontal axis and the tangent? Because if I know the tangent, I would definitely know what's the direction of the velocity, because the velocity is always aligned with the tangent at that moment. And look at this. Well, the tangent is, take the formula, make the derivative. Okay, so if you make the derivative of the path at that point, I mean, if you take dy dx, it's going to be, well, it's going to be, what is it, 2 times divided by 20, just do it by hand, x, and then if I substitute x here, you know that x is 10 meters, then I get to know that the y divided by dx, I mean that derivative, equals to what? This is 1 divided by 2 divided by 20, this is 1/10, multiplied by 10 is give me 1 here. And then if I take the angle of these two components, let's put it in the same fashion we know how to do it, then definitely, if I take the inverse of the tangent to that number, it's going to give me that at that moment, the orientation of that line is 45 degrees there. Great. What's next? Well, let's continue. Let's get to know the path. And remember that we said that this one here was written in a different way in the question. Actually, you can find this one here also as y prime or y to this. So also dividing with x. This is the same way to write it down. And then it's perfect that they are giving us the path, how the path is in terms of an equation, because now we can take that path and take the first derivative here, which I did it already, but is represented here. And then we can take the second derivative of that term, which is simply this one here. And then when we say, okay, what happens when x equals 10? Well, the radius of curvature at that instant is 28.28 meters. Meaning if I have something here, and this is the radius of curvature, or point something, point O prime here, then you could say that, let me go back to this 45. Yeah, more or less like that. So this is the radius of curvature of that skier. Because that's going to allow me to divide the acceleration into the tangential component and into the normal component here. Now this is presenting a very new notation for you. So it's written that the acceleration of the skier at point A equals to a tangential component and a normal component. This is the AT, and this is AN. Now, this representation here is bolded, meaning that this term here, UT and U sub n here, are bolded to indicate that this magnitude here is associated with the tangential direction, and this magnitude here, bring it back, this magnitude here is associated with the normal direction. Let's remember that acceleration is a vector that has two components, one in tangential direction and the other one in normal direction. Yeah. So this only shows that, hey, you know what? This U sub t is, this is tangential direction, bolded. And this U sub n is, this is the normal direction. This is why it is bolded. And the term here, A sub A here, is bolded also to represent that this is a vector. Vectors have magnitude and have direction. And I have written vectors such as, you can have it bolded, or you can have it something like this, with a line on top of that, meaning that it's a vector. So there are different ways of representing this. Now, okay, let's try to find out this vector. So this vector, the acceleration vector in this case, is the tangential component, which is the change of the velocity in the tangential direction. And what's the change of the velocity? Well, that's already given here, because you're telling me that the velocity is changing or is increasing at 2 meters per square second. The direct relation between the tangential acceleration and the velocity is 1-to-1, meaning that whatever changes that magnitude is going to affect directly, or it's going to affect, it's going to affect directly the tangential component of acceleration. That's why you have 2 here. But now, in the case of the normal component, you have to use the instantaneous value of the acceleration at that point, which is 6 meters per second, given by the formula, divided by the radius of curvature, which was calculated before here, and that, well, the first one to the square, and that's going to give you this value here. So you have the AT and AN, tangential and normal component. Then if we take this reference system, TN system, and draw it here, you're going to have 2 meters per second in the same direction of the velocity, and is pointing in the same direction also because it's increasing, meaning that it's positive. And then you have the normal component, which is always pointing at the radius of curvature or the center of the radius of curvature. And that's going to form the total vector of acceleration, which was already calculated here. The only thing remaining is to calculate this angle phi here. Say, okay, now tell me how much is this one. Knowing that from the horizontal to the tangent, we have 45 degrees. Definitely, I know how to calculate the magnitude, the resultant of two components by using the Pythagorean theorem here, given me here. And then I know how to calculate an angle, orientation angle between what we consider the x-axis, measured to that. So we have it here, and we have this 57.5. So meaning that we are taking this as our, let's say, temporally x-axis. So that's why it's giving me this phi here. It's giving me this 57.5 because it's calculating, taking kind of starting from this point to this point here. But what's the real orientation of the acceleration vector, but with respect to my horizontal axis, which is x? Well, your horizontal axis is this one here, meaning that I have to take this, let's call it in this way, try to subtract this 45 degrees from this one here to give you how much it's going to be pointing downwards, meaning this angle here that we just calculated is with respect to the normal direction or normal axis here. But if I wanted to know what is the angle with respect to the horizontal angle, then I need to subtract this 45 degrees. I hope that makes sense. That's why it's kind of when it's represented here as acceleration, it tells you that, yeah, the acceleration is pointing downwards, 12.5 degrees. This one here. And definitely the direction of the velocity is 45 degrees or downwards, and the direction of if I wanted to know the direction of this angle of the tangential component of the acceleration, is going to be also this 45 degrees. What questions do you have? Yeah, I have a question. Could you repeat why we have to subtract 45 degrees? Yes, yeah, that's a very nice question. Because we need to give an answer about the direction of that magnitude with respect to the horizontal axis. So first, let me just move a little bit this one here. Can I make this bigger? Maybe not. Well, let me see if I can make it a little bit bigger. Just a second. I want to copy this here, and let me bring it back here. Maybe where should I put it? That doesn't, yeah, here. Okay, so if I draw a horizontal line, which is the reference that I need to mine, because that's what they're asking me, a horizontal line should be something like this. Yeah. We have as a property from triangle or geometry of these lines that this angle here repeats here also, isn't it? This one here is also 45 degrees. So if I know that this is 45 degrees, and also you can repeat it also, this is normal to it, meaning that this is also 45 degrees here. So how much is this small segment here? Sorry. So you just take this whole angle and you just subtract by 45 degrees, and it's going to give you this small piece here. This is 45 degrees here. I hope you get to see it now. Great. You see, now things are getting deeper and deeper into this whole combination of stuff, geometry, algebra, arithmetics, and stuff. Now it becomes more complicated when we go to more, yeah, it becomes more complex but doable. We just need to keep in mind a few principles in here. Now, what happens when we treat these problems or certain types of problems by using cylindrical coordinates? They are cylindrical because we are in the mostly working on the plane. If not, we were talking about spherical coordinates. And this is, personally, this is one of the type of coordinate system I hate, but we have to deal with it because they simplify things for us. But I don't know why I have some certain negative thoughts about this one, but I have to live together with these ones. All right. In the plane, the cylindrical coordinate system is represented by two components or two coordinates, r and theta. So what is this? For example, if you had a circle, try to draw a circle here, and then let's remove the filling. Yeah. The typical representation of a particle, let's put it in that way, draw here. Of a particle at any point, particle P, is going to be represented by a radius and an angle here. We use, take this as a very high level concept of what are reference systems for. We use reference systems to be able to locate particles in a space. If we're talking about the plane, our reference system has to meet certain conditions to be a reference system. There are a few conditions to it. It has to have an origin, it has to have coordinate axis, and it has to be able to that those coordinate axes are independent from each other. So that's a very high level concept of what a reference system is. But if you say, why do I need reference systems? It's basically because you need to be able to locate particles on the space you are working. If you are working on a plane, it means that a cylindrical coordinate system, which uses radius and an angle theta, these two coordinates are more than enough to describe the position of a particle in time or anywhere in the plane. As simple as that. Cylindrical coordinates. When do we use cylindrical coordinates? It says, well, this is useful in applications where a particle moves at a certain angular velocity. So now we can talk directly as the center of rotation of the particle. The path or the radius of curvature, let's say, might change with time, no problem. But there is something that is very important. Usually we use cylindrical coordinates when with specific types of machines that the particle is forced to move at a certain way. And now when we talk about cylindrical coordinates, then as we talked about velocity in the x, y directions, we talked about velocity in x, velocity in y, because x and y were my two coordinates. Now that in my cylindrical coordinate system, r and theta are my two coordinates, then it's possible that I can extract from those two coordinates also kinematic magnitudes. And for example, the variation of this angle theta with respect to time that can be represented as this one is called angular velocity. And the variation of the angular velocity with respect to time is also called angular acceleration. Angular because it depends on the angle used in the description of the movement. Similarly to the x-y components or rectilinear movement, we could write that this, is a double derivative of the angle, the angular change with respect to time. And that's why you have this type of representation here and this type of representation here. It gets a little bit more complex, but the good thing about mechanics, as far as I have noticed among the years, is that mechanics is based on strong and well-defined principles. And if you follow those principles, you are not going to have any troubles in solving these type of problems. Sometimes, if you get to see subjects, for example, like simulations of a mechatronic machine in your master studies, there, the concept of movement of a particle or movement of a rigid body that we are going to see right here, these concepts are extended to a very more, let's say, sophisticated way of solving these type of problems. And what I notice is that you don't need to think too much to apply those principles. If you know the principles and you apply those principles just blindly, you're going to get the problem solved without any issues, because I've done it like that. You just need to know the principles. Then cylindrical coordinates, also referred as polar coordinates, those velocities, like the resultant of the velocities, you can also apply the Pythagorean theorem to calculate that resultant in terms of the values represented as velocity or values represented as change of these angular or radius coordinates. The same happens with the acceleration. Look at the description of the velocity, and accelerations depends on radius, the variation of radius, angle, and variation of angle. So perfectly fits into the concept of using a reference system with coordinates, radius, and angle to describe the movement of this particle. It's counterintuitive for us because we have been dealing with XY reference type of system all our life. In this case, it might be new for some of us that how can you represent a coordinate system that is kind of weird, it's just a radius and an angle. So, but it happens. And it's actually, I have to admit that it's a very good tool to simplify things. Let's take a look at a problem applying these cylindrical coordinates. So now we have some sort of forced movement here. So we have a rod OA that is rotating around this vertical axis here. So you see now that, for example, the particle, the collar here, B, is located at a R distance from O and at an angle theta from this kind of axis represented here. It says the rod OA is rotating in the horizontal plane such as theta equals t squared. So when they have this written like this, what it's telling us that at t equals 0, just as a simple example, at t equals 0, theta is equal to 0. At t equal to 1, then theta is equal to 1, meaning that theta changes with time. And if theta changes with time, it means, or it validates, that this is rotating at a certain angular velocity. And depending on the function you are using here, it can also validate that there is an angular acceleration also included in the process. If the function you use here to describe the angle theta, we're saying that theta equals t to the power of 3, and this function is twice differentiable, it means that there is existence of an angular acceleration. And this function is twice differentiable, because I can take one time differentiate this, or the one time derivative of this, and then I can take another derivative of that, and it's going to be existing. So it's going to exist. And if so, then there's going to exist an angular acceleration. Meaning that, yeah, we have angular, not only because of this, we have angular velocity, but we also have angular acceleration. Interesting. But now this said the color B sliding outwards along the rod so that R also changes with time. So meaning that this color here is moving in this direction, kind of following the rod, following this law, let's put it that way. And is this formula here twice differentiable? Yes, it is. And then means that it might be possible that we're going to have a velocity, linear velocity of this color here, and we're going to have a linear acceleration. I call it linear because if I forget about the rotation of the rod, the only thing remaining is a linear movement of the color B along the rod OA. Okay, now that I have cleared those concepts, I say, okay, tell me now, what's the velocity of color B when t equals 1 second, and tell me what's the acceleration of color B when t equals 1 second also. Now, the complex thing here is that B, or the movement of B, if you can see it, is comprised of two independent movements. If I forget about the rotation of the bar, then it's pretty easy to calculate the velocity and acceleration of B. But the thing is that while the color is moving, this bar is also rotating, meaning that the movement in the color B has, let's say, two big causes. One is the rotation of the rod OA, and the other one is the displacement of the color along the axis formed by OA. So you have those two main, say, terms that are forming the velocity and acceleration of B. When we start, let's say, having particles that are affected by different independent movements, things might get a little bit kind of more complicated. But again, if we follow the principles that we are going to show here, it's going to be easier to put a wall between those independent movements and analyze what's happening with one and what's happening with the other one, and then at the end combine them together to say, well, at the end, the velocity of this color B and the acceleration of color B are this. What questions do you have? All right. What we get to know or given is that the radio, or this distance from O to the color B, changes at this rate. Meaning that when t equals 0, the color is going to be at 100 meters from O if I just walk on this along this axis here. If I walk here, this is going to be at 100 meters. Millimeters, sorry. If I take the derivative of these parameters here with respect to time, then at t equal 1 second, this color B is going to have a velocity of 200 millimeters per second in this direction. But again, this is the velocity of the color, imagining that there is no any rotation here. That this rotation, this is just this rod OA is fixed, and this color is just, the only movement of the color is just moving like this, in this direction. So if I forget while we are revising this part of the calculations here, I'm forgetting about the angular movement of the rod. I'm just saying, you know what? I am standing here. How do I forget that that movement is there? Well, I'm just standing here and I'm rotating with the bar. So the rotation, for me, it doesn't exist. If I am standing on the rod OA and I'm rotating with the rod, then what I'm only seeing, and I want you to imagine this because this is key, is that the color is going away from me. For the color and me, the rotation does not exist. How can it be possible? Well, we are sitting on Earth. Earth is rotating and translating at spectacular speeds, and we just don't see it. We just see it because the sun goes at certain times and so on. But we don't, for us, our frame of reference is Earth, and Earth, even though it's moving and rotating at spectacular speeds, we don't consider that into our calculations at all. So in the same fashion, I can say, well, I am going to minimize myself. I'm going to jump on the rod, and then I'm going to acquire or have the same rotations of the rod, meaning that if I take a look at the color B, the only thing I'm going to see is that color B is going to move away from me. That's it. And it's going to move away with this velocity. And if I differentiate that, it's going to move away with this acceleration. And it's going to be at that point at 100 millimeters from me. That's the only thing I'm going to see. What questions do you have? All right. Now, when we go to the part of the angular movement, this part here, what I'm doing is that I removed myself from this and I fixed the collar to the rod. And then if I fix the collar to the rod, it's not moving anywhere. So it's just an oversimplification I'm doing for reasons of explanation. And I say, well, at t equal 1 second, this angle is going to be 57.3 degrees. The angular velocity is going to be 3 radians per second. And see, we're not talking about degrees here. We're talking about radians because that allows us to multiply between units. And it's going to be, let's say, it's going to give us the results in the right, correct order. And if I differentiate this again, it's going to give me that the angular acceleration is going to be 6 radians per second. So this is omega, this is alpha. But now the reality is that both movements are concurrent. They're happening at the same time. How do I combine, superimpose the effect of both? Let's see. I know that velocity in vector form can be written in this fashion. I believe it comes from this, something like this. These two terms. If I forget about the square root, then this would be expressed in those, sorry, no, in those terms here, actually. Yeah, actually, those two terms. So in the radial component, the radial direction, you have a velocity, and then in the angular direction, you have another velocity. That is, you have a velocity due to the displacement of the rod, of the collar along this axis here. This is r dot, and then you have another velocity due to the rotation of the rod, and this is called r theta dot. And that is going to form, also always these two vectors are in the plane. This is going to form the velocity vector here. V as a velocity. And I take this one here to form this term here. Then I multiply the radius times the angular velocity of this to give me this term here. And I have the vector, velocity vector form here. And guess what? If I wanted to have the magnitude, are they asking there? Velocity of the color? Well, this is the velocity of the color. Yeah. If I want to have the magnitude of this vector here, velocity vector, well, I take these two components, put it into the Pythagorean theorem, and then if I want to have the direction of that or the orientation of that, it's going to have, I'm going to take those two components, I'm going to give me this angle here. That we know how to do it. But now this is a little bit of a game here. So why the angle is not 56.3 degrees, the orientation, but it's 114 degrees. So let's go back a little bit. Why the orientation of this one here is not the one that was given to me right away. let me copy this one here. I hope that we all agree that this is the way it looks, like this. When I calculate the orientation of this resultant vector v, I used this term here as adjacent side, and then this term here as opposite side, meaning that this angle sigma here is this one here. But our reference systems start from this axis here. So I have to add the initial angle that I'm having, which is 57.3, and add this small angle that I have just calculated. That's why the final angle of the velocity is the sigma, which is the one that resulting from using the components of that vector and adding kind of the angle at the position of the rod at the moment. That's why it's giving me this 114. I hope it makes sense in this, because sometimes it's a bit weird, but we need to keep track of what are we calculating with respect to what, so we can give the proper answer. If we move to acceleration, it gets a little bit more complex in the formula, because this is the radial component of the acceleration, and this is the angular component of the acceleration. We already have all the ingredients for that were calculated here, this part and this part, meaning that we could use those terms to calculate what's basically that acceleration vector. It says that, you know what, the acceleration in the radial direction axis is minus 700, meaning that if it's minus, I would assume that anything in this direction is positive on the radial side. So this acceleration of the collar goes in this direction. And it says, but now the angular part of it is like this, is positive, meaning that is something that goes like this. So this is the angular component, this is the radial component. Let me copy this because I know that I'm going to use it. Now, if I wanted to know the magnitude of it, well, I just have to sum the squares of those two terms here, and square root of that. Pythagorean theorem is going to give me the magnitude of the acceleration, which is going to be something like this. We're about to finish now. And then the angle of this vector here. And the angle of this vector, how much is it? Is 68.7. And what's my reference system? My reference axis is the one, by this, or that has this, the component that has these 700 units here, which I equate with this one is something like this. So is this angle here. But then what's the angle to go from here, if I wanted to do something like this, from here to here? I put it in another color. Well, this angle, how much is it? Well, it is 180 degrees minus the angle that I just found is going to give me this small piece of angle here. This is 180 minus phi. And then this small piece of angle is theta. That's why the angle is formed like this. And then the final angle of this acceleration vector is 169. And this is the last slide. New concepts, new terminology, new nomenclature, but it's going to build up and build up as we progress in the course. What questions do you have? If not, I wish you a very nice week, success in your homeworks and tasks, and hope to see you next week with another topic that is related to what is becoming a little bit more, say, Laborious. It's called Kinetics of a Particle. So we're going to talk about force and acceleration. Thanks for being here. It was nice to have you, and take care. See you next week.